hyperMILL tool database. One of the most powerful tools inside of hyperMILL software that whether you're just getting started or you're a more experienced user, you can probably get a little more out of. My name is Mickey Jacobs. I'm a 5-axis programmer working in prototype and research and development. And I'm by no means an expert, but I am fortunate enough that I've had some time to dig into this. I've had some guidance from some people inside of OpenMind and some superpower users, and I thought we'd take a little bit of time and talk about some of the features and explain a few things because this is probably the future of your programming, whether you know it or not. And let's dive into that and we'll come full circle and kind of try to explain a little bit better why I anticipate this is going to be not just a powerful tool that you have access to, but a powerful tool that you will absolutely need to be using to its fullest if you want to survive the next 15 or 20 years, maybe as software gets more intuitive and we rely more on feature recognition and almost automatic programming. So you'll see we're working inside of 2020.2. Now this is coming out January 12th. Sorry about that. And uh, we have the 2021.1 release already. There's been some changes under the hood, nothing real significant. Namely, it's on the hypermill side. We've gotten support for some of the undercutting tools that we could always have defined inside of hypermill, but didn't actually have toolpath support for those tools outside of things like free tip geometry. So we're going to work in 2020.2. Um, you can file and create a new tool database. This is what you'll see. I just gave it a generic name here. You notice the database is created in SQLite. Now, for most people that it doesn't matter. For bigger shops, it gets a little bit trickier because SQLite, when it's operated remotely, so if you put it on a sort of network server, depending on network's configuration, and especially we have some people that are using this software, some power users that have multiple locations across the country, it gets a little bit tricky the way that SQLite actually kind of updates itself in the background. So you could have your sort of lead programmer, maybe you have someone dedicated, if you're fortunate enough to have that kind of time and personnel, to building out a robust tool database, and they're kind of making updates onto it. They might see the updates in real time, but other people trying to access the server might be confused because tools they expected to have been built out don't show up there. So the advice I've received kind of goes for the tool database and your projects and everything. Keep it all as local as possible. Sort of the more complicated your network grows, the more this sort of gets a little buggy. Now, there are some features in here that I'm not really qualified to talk on. There's some synchronization tools where you can kind of point to where the database is at and try to sync things up a little bit more, but that might be a topic for another day. Let's kind of focus on what it takes once we have our new database created. Where do we go from here? So if we right click on the tool database, we're going to see pretty much what's important right here. So when we go to build out a tool, we'll use the new tool function. At first, we can actually kind of um, figure out what tools we use most commonly. We can set those as defaults even. So every time that we go to create a new tool, maybe they have some features saved already that are important to us. But mostly the bread and butter's down in here. Our cutter materials are materials, couplings, technology usages, coolants, and formulas. The rest of this stuff is certain utilities. Until you really get on top of this stuff, you aren't going to be focused on custom data classes. The import and export function is just like what it sounds like. If you have some tools built out in this database, you want to export them. and then re-import them into a separate database or use the data elsewhere. You have that function here. The report is not too different from the report you can generate from the utility function inside of hyperMILL. Now that just got a pretty big update in 2021 where the tool report now actually leverages the power of the automation center now. It's a little fancier. You can do some more stuff with the data. This report, believe, is still based off of the legacy HyperView product. In all honesty, I haven't played with the new report function that much. The other important option down here is our measurement system, metric or inch. It's a big deal because once you commit a tool to a certain measurement system, you can't change it. You can copy the tool, and then you have some options when you copy or duplicate the tool. But once that first tool is created, you're married to that. Now, there's some other ramifications as well. While XML is supposed to be a neutral exchange format, if you've used other CAM softwares or if you tried to import XML files before, you may have found that it's not as neutral as you think. And good, bad, or otherwise, hyperMILL requires the XML file to be laid out in a certain way to really work correctly. Um, so there's going to be some issues on the XML side and also the DFX. So if you're using DFX line geometry to define a tool, if the vendor created it in a different measurement system than what you're using, it's not going to work, and it's actually kind of a pain in the butt to get it changed over as well. So keep that in mind. Once you commit to one of these systems, you're married to it. Now, we are in the automotive sector, so all of our stuff's in metric. So I'm going to keep this metric system selected, and we'll jump into the first thing, and we kind of go in order here, and we'll get where we want to go. Cutter materials. What are cutter materials? Well, if we select this, we're just going to get another blank box. We can come in here and we can go new. So what is a cutter material? A cutter material is going to be a sort of name to drive all the data for a certain tool. So in and of itself, it doesn't do anything. It doesn't mean anything. The way that we've decided to use it is kind of we'll say by list number. So almost every major manufacturer has a list. OSG or Goering are great examples because people use those taps all the time. They might say, oh, we like list XYZ tap or list XYZ drill. Other vendors, they might have a name for the series. We use a lot of SGS tools. So, for an SGS tool, let me turn around and grab my catalog over here. S carb is their aluminum line, but for each S carb, there's a series 47, there's a series 43, there's a series 43 MCR. That's metric and corner radius. 43 LC, that's a long tool with a neck on it. We want to kind of identify these different series of tools or different groups of tools or list numbers of tools with a unique name, because we're going to take this name and we're going to apply all our feed and speed data to that name so that as we create tools inside of the database, we can say, hey, this tap is from this list number and this tap is from this list number, and one of them has a alt encoding on it and one of them doesn't, so the surface footage is higher on this tap, and maybe this one's bottoming and this one isn't. The data that we decide to select for our tool is all going to come back and kind of be tied to this list. So let's start with something pretty generic from the get-go here. We'll do an end mill. So I'm a metric guy. I got my catalog cracked open here. I'm going to go with S carb series 43 metric corner radius. So I'm just going to go, I'm going to call this the SGS series 43 MCR. And I could say these are solid carbide end mills, corner radius, uncoated. Okay? Boom. Step one. Step two, we're going to come back in here. Now, the next thing down is materials. So this is equally as important. Why? Because this is what we're going to drive all our tools with inside of hyperMILL. Everyone remembers when we build out a new job list, one of the parameters we can define inside the job list among stock, fixture, and part is what sort of material it is. So let's go ahead and say we're going to create a new material. Um, this is something you might have gone, well, we just got boxes done, something doesn't look right. I'm not sure if this is a 4K screen thing or what, but you'll actually see our data box is over there. It's just all the way on the side. So, right, so we're going to come in here, we're going to go down to materials. That's next on our list. Now, this is super important because anyone who remembers setting up a job list inside of hyperMILL knows that one of the things we can select is our material type. And when we define our tools correctly inside the database and we set our material correctly inside of hyperMILL, when we go to either build out tools or select tools, it's only going to show us the tools that we have set are appropriate for use in this material. Now, this has even more ramifications as we embrace some of the new technologies coming out with the software like Automation Center and the virtual tool. As we kind of look towards programming automation in the future, one of the things we need to be able to do is have a really robust selection of tools that a piece of software can easily figure out what's suitable and what's not. Again, all driven from the data here. Now in the 2020.2 release, we simply go up here, we can create a new material. You'll see on my 4K screen, for whatever reason, it puts the box all the way over here on the right, but we can expand the box. We can say, okay, this material we're going to define first is going to be aluminum. Um, we'll say uh, specifically this is going to be wrought, and we can even add some examples. We'll say it's also ISO N, and I like to put a little asterisk or star and say that that would be like a 5052. 6061, 7075. So we've kind of done three things here, and sometimes it's about thinking about other people, other programmers. Um, my boss sits right next to me. He's been programming CNC machines for like 15 years. I ask him what an ISO N material is, and he's going to look at you like you're speaking a different language. Um, so we've put some things here that are basically universally identifiable. Everyone knows what aluminum is. The chances are you're not going to get into trouble if you have a piece of aluminum in the machine and you select this, even if it was something cast or otherwise, you're not going to explode. But we put aluminum in here, we put raw, we put ISO in, and we gave some material examples. Whenever I'm doing this stuff, I'm thinking about the people that come after me and scalability, and the things that make sense to me don't necessarily make sense to other people. So this kind of covers all my bases. Yeah, it's a little wordy at the same time. Something else I like to do, I like to add numbers, and that's because you'll see this trend kind of follows in other categories as well. hyperMILL likes to do some weird stuff. Sometimes the menus are alphabetical, sometimes they're follow some sort of number sequence, and sometimes they just are in whatever order you created them in. So it seems like almost everywhere, if you add a number, you can organize things correctly, and I like to kind of see things organized correctly. So anyway, we have our material defined now. What's the next step? Well, we're gonna apply some default milling technologies. Now you'll see turning technologies here too. Obviously, we can build out. There's pretty robust support for turning tools inside the tool database as well, and we'll probably cover that maybe in a separate video. We're primarily a milling department here, so it's the thing I know least about, but it does have some pretty strong tools, especially for building out complicated 3D holders. So we'll get there. But for now, we're going to focus on our default milling technologies. I'm working in metric, so I'm going to select metric. Now, there's nothing here right now. We can even right click and you can see it's in the expand all mode, but there's nothing to expand. So this is when it comes back to our cutter material. Now, we're going to go ahead and apply a cutter material for this material type. Now you'll see that the thing that popped up is the series SGS Series 43 MCR, because that's all we have inside of our database right now. But if we had to find 200 separate, um, milling tool materials, they'd all be here. So we can say, okay, yep, that's the data. And now we get another drop-down menu. This is where the magic happens. So what we're going to do now is we're going to be able to take a manufacturer's cutting speed data, um, relative to the tool diameters that are important to us, and kind of put it in here and actually use this data for mathematical calculations for the tool. Um, this is where hyperMILL gets really strong. We can use basic surface footage and chip load data and actually do things like build out formulas for radial chip thinning or effective diameter of ball end mills, and it gets really, really strong. But it starts with this. This is the basics. The way the system works is it will apply these values automatically to any cutter built out in the database with this cutter material up to XYZ diameter. So if we say, we'll flip 2 pages in our SGS catalog here, and we're going to probably come to the data with all, or a page with all our feed and speed data. And sure enough, here we are. If we say, okay, they tell me for a 20 millimeter tool, we're going to use the slotting data to start. Or better yet, we can use the profiling data. They actually provide some high-speed machining data as well. Um, you need to kind of decide which data set you're going to use, because most manufacturers provide you at least one or two. Slotting has generally been sort of the great equalizer. If you had a firm grasp on your sort of slotting feed rate and chip load, it was pretty easy to figure out other values from that. But I like working with the profile now that I think about it. That's probably what I use most often. So I'm going to say, okay, I'm going to commit to their sort of profiling, and they've given me a depth of cut and a step over here too, which is going to be important here in a little while. But for now, my two takeaways are going to be that they want this tool driven on average at 610. Um, this is in metric, so that's meters per minute on the surface footage, and with a feed of about 0.166 per tooth. Now, if we walked away, what's going to happen is any tool from 1 millimeter up to 20 is going to be driven by this data. That's not what we want. We want to be a little bit more accurate than that. Unfortunately, in the catalog here, we have data for 3, 6, 10, 12, and 16 millimeter cutting tools. So I'm going to go ahead and say I'm going to insert one row above. Now, it automatically divides this by half. It doesn't do you much good. But I'm going to go ahead and say, well, I know I'm going to have data for 16, for 12, for 10. What else did I say? For 6, and for 3. Okay, my recommended surface footage, at least in the catalog, is the same for all of them. And let's work now top to bottom on the chip load. So on 3 millimeter, it wants 22 micron per tooth, 600, tenth and a quarter. Yeah, sounds funny saying a tenth and a quarter, but this is metric, friends. 144. I actually misspoke. That's 166 and that's 187. Okay, what we have here, our cutter diameter, our cutting speed, and our chip load. Over here are the functions for drilling. We'll use those for tools that are designed to work in the Z axis. We won't put them in here. Yes, actually, I believe these tools, along with a handful of others, can technically be drilled with, but most people aren't using an end mill to drill, so we're going to go ahead and skip that. So we can jump down here. Okay, we've saved that data now. Now we're not quite done yet. We're going to come back around to couplings. That's a really important feature that's kind of around based on ease of use. When we define the couplings between the end mill, the tool holder, extensions and tool holders, callouts and tool holders, it just means when we select a 12 millimeter cutting tool, we're not going to see all 200 holders we have in our database. We're only going to see the systems that are usable with that tool. Um, Technology usages is going to be important once we get our tool built here, and then coolants and formulas will come afterwards. Let's have a sneak peek at formulas. Formulas are basically, this is all the stuff that's driving our cutting data. Now, by default, unlike some of the others, this one has some data in here to get you going. The three big categories are feed rate, length, and speed. So for feed rate, they've actually defined a feed rate, and they've said what it's doing. So we have the default feed rate formula, some in feed formula, reduced, and drill. So we can look at these and kind of figure out what we're talking about. This middle column is the good stuff, okay? So when we select the FFF value, which is our base feed rate formula, what's happening behind the scenes is we're taking our chip load, we're multiplying it by the number of flutes on our tool, and then we're multiplying it by n, which is our speed. We can come over here, I'm sorry, that's the right arrow here. This is where we have all of our mathematical functions that we can use. Now, we're going to see some trigonometry in here, use of exponents. This becomes all really important when we start talking about things like effective diameter of a ball mill on a 45-degree angle. We're going to be relying on converting between radians and degrees, as well as some functions of arc cosine. But we can see here feed rate per tooth, feed rate per rev, cutting edges, spindle RPM, cutting speed, drilling feed rate, etc., etc. So these are all values that we can use inside of the formula area. And it's pretty nice too when we apply things that don't work. It's going to turn red. We're going to know we don't have a formula in there. And furthermore, if we mouse over it, it's going to tell us kind of where the problem exists. That seems like not a big deal now, but once you see the formula for the effective cutting diameter of like a ball end mill or bullnose end mill, it's pretty incredible how complicated that formula gets. It's important to know. Length, nothing in here for length. This is primarily used for things like, if we want to say a quick formula for 10% of the cutter diameter. So we don't always want to have to type in, the actual value in our tool definition page. We can create a simple formula, it's D times 0.1, and it'll automatically give us that 10% of the cutting diameter. And speed, so it's done some calculations here to get to spindle speed with the feed rate data we've given. So we have our surface footage times 1,000. That's the constant here for metric. Over the diameter times pi, and here you can see the inch equivalent. So let's jump in and create a tool now. So I would encourage you to take time, piece of paper and a pen, and think about how you want to organize your tools. There's a million ways to do it. There's no right or wrong way, but again, let's think about sort of the people that we're working with and what is going to be the most universally useful sort of way to do this. Um, there are a couple thoughts here. I've done it a couple different ways, and I'm still trying to figure this out. If you look at some of my own tool databases right now, I have 3 working databases that are built out 3 different ways because I'm trying to imagine, well, what if there's 25 people working with me and not 2? What would work best for them? Do I want to kind of just organize tools right from the get-go by materials? Do I want to organize it by the type of tool they are, a corner radius end mill, a square end mill, a tap, a drill? Or do I want to organize it by vendor? It's going to be different for everyone. It's going to kind of depend on how you organize your tools and how people access them. If your tools are like most shops and they're kind of spread out everywhere and maybe a little decentralized, then just organizing it by popularity, like, right, we always buy these tools from Helical or these tools from Fraser or these tools from OSG. So we'll do it by brand name. If you have a centralized tool crib, then maybe they're all organized by type. You have a list cabinet that just has 3 flute end mills for aluminum. um, in the end, we only need to put 1 or 2 pieces of data in the tools data area to make this really easy to use, because what you can see over here on the left is the filter tool. And ultimately, my goal is with every tool, as long as I get the EDP in there, which nearly every tool is going to have some sort of EDP, then all anyone with that tool needs to do is type in the EDP and they're going to get to this data eventually, even if there's like 20 folders and 7 levels, and they're going to figure it out. So for now, we'll keep it simple. Let's do a folder. Let's just call this um, just simply end mills. And inside our end mill folder, we'll do square, corner, uh, corner radius, or not. Well, apparently we have a, let's expand. I'm sorry, I had to that's an update thing. Sometimes you'll have to close and expand it to get it to update. And ball. So the tool we just created was, or the data we just inputted was for the Series 43 MCR. So that's a corner radius end mill. So I'm going to come into corner radius. I'm going to say new tool. And this is when we could start adding more and more levels. We could say, well, inside there, we're going to have an SGS folder. And inside the SGS folder, we're going to have a corner radius. Well, for now, let's just hop into it. Let's go with a bullnose end mill. So this is sort of the hyperMILL default screen we're going to get. We have a simple image over here that's kind of depicting what our tool looks like. We have the data relative to the geometry of the tool on the first page, and then the technology on the second page. This is all the good stuff. This is where we're going to take that data that we applied with our cutter material and our sort of surface footages and chip loads and everything, and actually turn it into really good usable data for use inside hyperMILL. But let's get it defined first. So um, we use a pretty unique naming function here, and it's kind of designed around really quickly being able to identify what sort of tool this is, even when it's buried in a magazine or something. But let's keep it, again, simple for this video here, and we're just going to call this SGS. We'll start with a D12 end mill. R, we're going to use 1.5. Now, EDP. I stick it in here right inside the name. So for that tool, it's going to be a 44814. I stick it right there in the end. Now, when I save my database, we'll get a couple more tools put in here. All I have to do in this name section is type in 44814. And when I have this default filter applied, I'm only going to get this tool. So it's going to make it really easy, even if I have a couple hundred tools in here, to get to this tool. The comment. Now, this data, both the name and the comment, can actually be queried inside hyperMILL or even displayed as part of your tool list or whatever. So you can use this for anything you can imagine, from a simple message on a through coolant drill that says, hey, make sure the mist extractor is turned on. Make sure that, the coolant comes on this drill. You know, if you have a bunch of different machines and you're using a bunch of different M codes defined inside of hyperMILL to make sure that the tool has through coolant, you know, maybe someone juxtaposed some M codes or something. So this is like one more chance for someone to see like, hey, this thing is supposed to have coolant running, or you know, this is a super extra long drill, so turn the rapid down a little bit. So you can put anything you want in here, and then actually kind of query the comment inside of hyperMILL, and as well as the name, and you'll see that data again. I'm just going to put something generic here. This is an uncoded SGS solid carb end mill. We'll say 3 flute. Okay. Now, it's a bullnose end mill and it's metric. Now, what did I tell you earlier? Once you committed to a measuring system, you'll see we can't edit this. A, because first of all, when we went to build this tool, we said new. We chose the type. That is good, bad, or otherwise something to be mindful of. You can't edit this or change this afterwards. Sort of doubly frustrating. Maybe you have a square corner end mill with the same geometry and you just want to copy the data. Unfortunately, that's not something we can change. Once it's defined as a bullnose end mill, we're married to it. Now we'll come down here to the geometry. Well, SGS is telling me this is a 12 millimeter tool and has an 83 millimeter total overall length. Now, we have the function here, Shank. The primary function of the Shank function is going to be identifying tools that have a larger shank than cutting diameter. But secondary, it works well in conjunction with the collar function, which if you have a necked tool, where let's say we have a 40 millimeters of reach, but just 20 millimeters length of cut, then we probably have a neck with a diameter a little bit smaller than our cutting diameter. We can use these functions together, and we'll go ahead and do that on our next tool. But this is a plain Jane, so we're going to leave it unchecked. What is the cutting length of the tool? So the effective cutting length on this tool is a whopping 26 millimeters. And down here, we're going to see the corner radius. This value exists because we chose it as bullnose, 1.5. Now we're not done yet. There's another function down here, which is the top coupling, and this is going to kind of work together with the couplings feature we covered briefly earlier, and that is that for kind of quality of life, we don't want to spend a bunch of time looking through a million holders that aren't suitable for this tool. So we're going to define what the top of this tool is, so that hyperMILL can kind of use that function along with our tool holders. So we're going to say it's a shank. Big surprise for circular cutting tools, your only option is shank. And it's going to have selected the diameter automatically because that's our cutting diameter. It's going to have used the shank diameter if we have the shank function active. And then we have our minimal and maximal length. So this tool could theoretically be inserted into a holder, um, you know, 83 less 26. You can do some math in here, by the way. But I know that with a tool this long, a 12 millimeter tool, I don't probably ever want it in the holder any less than maybe 25 millimeters. If I'm hanging it out more than that, yeah, hashtag job shop life, I'm probably going to get myself into trouble. So now, by default, when I go to build out this tool, if I try to tell it, hey, I want this thing to stick out, 59 mil, it's going to throw an error. It's going to say, no, 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 that's outside the parameters you defined for the tool. And when you come to that situation and that happens and you're like, crap, I need to stick it out more, guess what? While you have your whole tool assembly active, you can come right back in here and you can edit these values, and your little angry red box will go away. So I'm going to click save up here again. Once we close out of a tool, it'll save automatically, but if you've ever worked on a computer in your life, you know they're prone to doing weird stuff. So when that little save icon's active up there, if we click that, it'll keep our work saved. Now, onto the good stuff. Technology. Technology page. This is where all the magic happens. We're going to see some familiar jargon down here and up here. And the first is going to be cutter material. Now you remember when we earlier we defined, sorry, top level right click, a cutter material for this exact line of tools. So while we're in here, we can go to our cutter material and look at that. SGS Series 43 MCR, it's right there. If you had 500 different cutter materials, they'd all be there. We're going to put this on pause for a second. We're going to do a little bit of backtracking so that we can see the aha moment here. And that is we're going to come back to our top level here and we're going to talk about these technology usages now. All right. Open up technology usages. What are technology usages? They're how we're using our tools. In my current working database, I have like probably 35 or 40. It's actually gotten a little bloated and I'm trying to consolidate and go back now, but it's all the different ways we want to use different tools. And so let's go ahead and get going. What is our first usage going to be? Our first usage is just going to be with a traditional end mill like this. Let's say it's slotting, okay? And this is going to be full width of cut. I think for the slotting parameter here, full width of cut. So when SGS talks about slotting, they talk about it as an AE of D1, so full width, and an AP of D1, so 1 times the diameter. Full width of cut, DOC equals DC. This is just text. This is just flavor text, so that someone else looking at my slotting parameters are going, where the hell did he come up with this? And why is this? They can open up the technology uses and go, okay, this idiot defines slotting. What is slotting? Okay, so slotting for this guy is full width of cut and a depth of cut is equal to the cutting diameter. Since we're just going right out of the catalog, the other 2 parameters given are profiling. Sorry, no space at the end anywhere in the tool database. Add a space on the end, hyperMILL angry. So no spaces. And we're going to say this is side milling at, they're saying anything less than or equal to 0.5 DC, and we're going to say at 1.5 times DC. So they're basically saying anytime you're using less than half the cutter and more than or less than or equal to 1.5 times the cutter's diameter AP, you're in a profiling application. In reality, most people aren't taking a half cutter width step over because in most machining centers and most tool holding and work holding, that's not super practical or efficient anymore, but that's what they're giving us. And lastly, they have some high speed machining. So we're just going to say high speed cutting, and that is, and then this is the absolute opposite direction where they're saying that's going to be less than or equal to 0.05 DC, which now that's the other way. That might be great for cutting tools in steel, but for an aluminum tool, we're going to take more than just 5% of the cutter diameter step over because we can easily do that. And they're saying at less than or equal to 2 times DC. I'm gonna add my little time symbol. And this again, this can be whatever you want. The values in here don't matter. This is just flavor text, so we understand what's happening. So we've defined some usages for this tool now. So when we come back in here and we come to technology, we're going to jump down here for a minute. You'll see we have 3 cutting edges up here. That's great because this is a 3 flute tool. That's important because we know formulas like our feed rate are going to take things like the chip load and multiply it by the number of cutting edges. So having this wrong is a really easy way to destroy a tool. Don't ask me how I know. technology, invariant. So this is the sort of default milling parameters. When you don't have something defined inside of hypermill, you are going to default to the sort of invariant cutting data. We don't care about this. We're not going to use this. We're power users now. We're going to define stuff correctly. So we're going to come up here to technology. We're going to go add a material. Hey, look at that. Raw aluminum has appeared. Now, just like we've said before, if we had 50 different materials defined, we'd have a drop-down menu with all those materials. Now we're starting to see how this whole system is coming together. Where this is like super robust is having drills that are suitable for 10 different materials. We can take that drill, we can apply all these different materials to them, we can put in the appropriate data for those materials, and every time we are working inside hypermill, we can grab that tool and have this good feed and speed data and kind of increase that whole process reliability and air proofing. It gets really, really good. Usage. Now down here, we're seeing our usages that we just defined. Slotting, profiling, HSM. So let's start with HSM. Now, look at this, 0, 0, 0, 0, all of this stuff is blanked out. Moment of truth. We come up here, we select our tool. Look at this. Now we're going to drive our surface footage and our chip load from the data that we defined earlier. We connected our cutter material to our workpiece material, and now full circle, it's coming back and giving us data. And these values are the values defined in our formulas area. So we come down here, we saw these earlier. We're going to use the spindle speed that formula that we saw earlier as f of s. So now we have calculated our cutting speed relative to this feed rate and this chip load. Our feed rate, we can use the default feed rate formula. Axial and reduced. Okay, this is something that you're going to have to play with. For us, the way hypermill's working, kind of the way that we're set up, the axial feed rate might usually be the distance between the end of a G0 move and uh, the end of a G0 move and the workpiece. It's that distance. If you like doing things fast, then you probably don't want to use a reduced axial feed rate. As a matter of fact, sometimes I actually increase the feed rate because, especially in certain Z level operations, if it's not in a part where you can easily spiral down or something and that tool's coming away from the workpiece a lot, everyone's seen a machine where you're ball end milling on a 3D surface and it goes into the cut and it cuts across and it comes up really slow and it goes back over G0 and it comes back and it feeds in so slow. Then it cuts across and it goes up again, G0, and then it feeds and it seems like it takes forever. So if I know that I have good code and a good tool path and my end mill isn't just going to be plunging into the material, I might just use my feed rate formula here. I might use my feed rate formula multiplied by some factor because I want to meet that G0 with a really fast feed move to get my tool back to the workpiece as quick as possible. For now, because we haven't defined much else, I'm just going to go ahead and use the feed rate function. Reduce feed rate. So this is something you have to play with a little bit. hyperMILL will automatically reduce the feed rate dependent on a handful of variables. It could be something as simple as defining an engagement angle for reduced feed rate. Sometimes I like to calculate at what angle the cutter is engaged more than a certain amount on the diameter, yada yada yada. It usually works out to about 30 some odd degrees. Um, hypermill reduces the feed rate by default during some functions, um, usually cornering and stuff like that. So there is a reduced feed rate formula built in here. I was gonna say I thought we could mouse over it to see, and there we go. So if we mouse over, we're gonna see basically they're doing 70% of the feed rate to achieve the reduced feed rate. If you do hover over these, you can see kind of the math behind them. Now, Again, not done yet. What else can we do in here? We can set the infeed width and infeed length. Now we're getting into the good stuff. Why? Because the inside of hyperMILL, when we're doing certain operations, we can drive the tool with these variables. So how about doing new optimized roughing, and after you select the tool, you're virtually done because it's going to automatically, you're going to have HSM selected as the usage type. You're going to have right clicked inside your width of cut and step height, and you're going to have selected those values, right? And you're going to have saved that as a default. So now that every time you open up optimize roughing, as soon as you select a cutter, it's automatically selecting its infeed width and length off of the data driven by that cutter, right? I mean, you can even go so far as to define the amount of rest material to leave as a function of the step over or the cutter width or cut. You can do some really neat stuff, um, all driven from this data. So we'll take one step back here. Coolant, you're going to have defined some coolants. Inside your post and hypermill. And the way that works is you can say, okay, in hypermill or in your post build, you're going to say coolant 1 is M8, coolant 2 is M7. If you're a DMG guy on a Siemens, you might use M7 and M72 or 73, and M8 and M72 and 73. And those are all going to be tied back to just simple numbers 1, 2, 3, 4. And these are where those numbers are coming from. Um, just make sure that all your stuff is jiving. Make sure that through coolant in one post is coolant 1, and through coolant on one of your other machines post is coolant 3. That's bad juju because that might be defined as air for that tool. We can define our coolants. We can take a step back here for a second. Right on this screen here, we can add new coolants 3, um, external air. We'll say this is DMG air blast. Oop. And then again, in your post, you'd say, okay, let's see if I can get this right. So for us, external air blast on a Siemens, on a DMG would be M8 for external usage, and M72, I believe, is the air blast master. And M7 and M72 would be for internal air. So back to technology, so we can define our coolant there. You can do some other cool stuff with that function too, because guess what? Those numbers are just tied to M codes in the hypermill post. So you want to turn on the chip conveyor automatically? Great. Coolant 7 is chip conveyor. Now you just need to define coolant 7 as your chip conveyor M code. And now, whenever we're high speed machining, guess what? We just turned on coolant and the chip conveyor at the same time because we know we're going to have a lot of chips. Oh, you know the code for your mist extractor. Let's make sure that anytime we turned on through to coolant that the mist extractor also turns on. It's as simple as defining those generic numbers and then tying those numbers to M codes in the hypermill post. Super powerful. Back to HSM. Okay, HSM. So they're saying they want 0.05 DC. Um, oh, sorry, I don't actually have a formula built out in here. So we're gonna have to do some math. We can say 0.05 times 12. Okay. That really doesn't want to do any math, does it? Okay, so that should be 0.6. And infeed length is, they define it as 2 times the cutting diameter. Now let's make sure our length of cut supports that because that's totally on us. So we can go up to 26, so 24 is fine. Don't get yourself in trouble there. Plunge angle. These tools will just about drill, but since we live in the real world and chip evacuation and chip welding's a thing, let's stick around somewhere between 5 to 7. We'll go conservative with 5 degrees. And a max angle for reduced feed rate. Sometimes your cutter, sorry, your vendor will provide some data for that. Um, You could also theoretically kind of draw up something simple on with some lines in hyperMILL and figure out kind of at what angle we're exceeding our sort of infeed width. Um, and use that angle. 30 degrees seems to work pretty good. The way that this is calculated, I or used is sort of up for debate. I've asked a couple of different people and gotten slightly different answers each time. If you're using high-speed machining, using the volume mill function, you're using most of the default parameters. You're not really going to get into trouble with this, even leaving it as 0. Now, there's one more thing we have to do. When we define this data here, we defined it as the profiling data. So we have some options. Um, in another video, we'll take the time to show the build out of some more complex formulas where we can actually, instead of using this default feed rate, we'll apply some chip thinning formulas where we can use this data and actually drive the high-speed machining function. Alternatively, we could actually disconnect or unlink this data and use the data direct from um, SGS as provided. But there's a reason we kind of want to keep this link and actually modify the multiplier. And that is when we're running these tools, we might find out that there's some more headroom in there. And instead of going in and changing 50 million usages, because we've finally built up our tool database to include 200 tools and each tool's got 10 usages, we can just go back to where our materials are defined and select this cutter material and just bump up the feed rate a little bit. And that's going to modify the data for all of our tools that use that value. So let's actually look at what they say here. Now, they're saying that for high-speed machining, they're going to keep this feed rate. No, I lied. They're going to, sorry, keep that speed. They have the surface footage here as 1,000. So let's take 1,000 and divide it into it 610. Oh yeah, big surprise. It's 1.6, and let's drive that with a simple value here, and then we'll find out. Well, we got a little closer. It's actually 1.64 is the value. And look at that, we're at 1,000. So now, like I said, if we find out there's some more room in these tools, or maybe it's a little too much for our machine and we need to back it off a little bit, we can just change that master value, and we'll actually do an example here in a second. And we're going to update all of our data because we didn't break that link. And then on the feed rate side, it wants to see the feed rate on the 12 millimeter tool at 0.336. So again, let's divide 336 by 144, and we're going to get 2.33. So these are some pretty robust parameters. So you're going, oh my God, 26 friggin' meters a minute at 26,000 RPM. There's no way my machine can handle that. Don't worry, friend. This is only the beginning, because when we take this tool and we mount it and we connect it to a holder and we create an NC tool, we can actually define at a couple different steps along the way where our maximum feed rate is or spindle RPM for that machine. And this is the beauty of it. hyperMILL will adjust these values appropriately and in sync. So we know that if instead we only have 12,000 RPM available, it's going to cap our spindle speed at 12, and then it's going to drive our feed rate off of this new spindle speed so that we're keeping our cutting data good. We've just lowered to the parameters that our machine is capable of. So we define two other usages for this tool. So we can come up here and add usage. So we've added slotting and profiling as well. You're going to see that, yeah, we have to go through again and reselect our formulas. Now, after we've created this tool, if we're happy with these formulas, we can duplicate this tool and change the values for diameter and length of cut, and it will keep all this data in here. Unfortunately, by default, we, at least to the best of my knowledge, kind of end up with empty formulas again once we have to modify the parameters past a certain point. Or obviously, we might change if we have a major change in cutting diameter. Some of these values might change. while hyperMILL is automatically going to change our surface footage and feed rate based on diameter because we defined it in our material setup, things like the infeed width and infeed length, it's agnostic to. It doesn't know anything about that. We put that data in there. So once we start driving even those values from formulas that we've created in our formula table, it gets a little easier to copy tools. So if we always want to take, 90% of the flute length and 10% of the diameter as a infeed length and step over respectively, then yeah, we can just shake and bake. You can just keep copying tools and just change the diameter on all of them, and this data is all going to be good. But the reality is taking, 2 times or 90% of the flute length on a 3 millimeter tool and 90% of the flute length on a 20 millimeter tools could, yield vastly different results. So we might end up coming in here and modifying those parameters for our other tools. So let's keep going with this. You're going to see here that these have defaulted back to the stock values. I missed this one here. For reduce, we're going to use the reduced function. Did I use it there? Reduced. Okay, slotting. What did we say? So slotting is going to be one-on-one. So for slotting, we're going to say 12 millimeter in feed width, 12 millimeter length. And for profiling, they're saying 1.5 times diameter length and about half the width. We can, again, change our plunge angle 5. Excuse me, 5. We can put in a max angle for reduced feed rate. So the profiling data, that was our sort of base data we started with, so we know that's good. Obviously, the slotting is going to be a modified parameter. So again, we're going to take this. They're saying for slotting, they just want to see 490. So again, I'm going to take 490 divided by 610. So we're going to use 0.8 as the multiplier on that. We're right around 490 now. And for the feed on the 12 millimeter tool, they just want to see 140. Oh, look at that. Wouldn't you believe it? They're confident that you can take the same chip load, whether you're in a full slotting situation or profiling, so long as you meet it with good surface footage. All right, we're going to save because we always save. Now we have the beginnings of a tool. Let's take it one step further, and hopefully this video isn't getting too long, and let's talk about holders. We're on the holders tab. We got nothing here yet. Let's build a holder. From here on out, we're doing it easy mode, man. We jumped on the Heimer website. We got our holder solid model already. We're going to go to this geometry area. Click the little pencil and create new geometry with hyperMILL tool builder. This is awesome. We're going to open the tool builder up. This is the interface. Looks just like HyperCAD S. We have a lot of the same tools, but it's super easy to use. We're going to pick our tool holder that we just downloaded. And boom, we have our tool holder. It doesn't get any easier. It's going to walk us through step by step. What body are we using? We're using that solid body. Next. Is it oriented correctly? Yep, that's the machine side. That's the workpiece side. Yep. Where are we mounting? Well, we're going to start with the top. That's where it mounts to our spindle, and that's where it mounts to our tool. We're done. There's our solid revolved. Ready to go. We click our export tool. Boom. We're back inside hyperMILL. We're ready to go. I'm going to call this Heimer 12 millimeter shrink power L130. Now, we mentioned earlier that we could apply some constraints to our tool to make sure we don't get ourselves in hot water. So let's go ahead and define our maximum spindle RPM as 18,000. Let's go ahead, excuse me, and say yes, this holder is suitable for cooling through. Let's say, well, we need to define a top coupling and a bottom coupling. Just like over uh, in the tool definition side, we can come up here. There's our couplings. We skipped over this earlier, but now it's time to use it. Let's open up couplings. There is a lot to take in here, but basically what you need to know is things that match can go together. We like to use Morse Taper as our catch-all because it's sort of a nothing. It doesn't have any value or data on the hypermill side attached to it. So we can freely define an ER32. No, that's not even a great example because technically we have collets that work fine. Milling chucks with straight collets. Or maybe you have some, we're just trying out now the MST two-piece shrink fit holder. It's got its own unique coupling geometry. So I'll use Morse Taper to define both the bottom side of the master holder and the top side of the extension, and those two will always mate together. Let's go ahead and define a shrink fit diameter. Let's say new. We'll call this Heimer 12. Why do we want to call it Heimer 12? Well, if I have some Heimer holders in here, but I also have some Parlix and some Techniques, there's a value here that's important. Maximal length. Well, my Parlec holders, I can put a tool in those up to 50 millimeters inserted in. But on my Heimer holder, I can only go 45. So to keep myself from accidentally building up a tool in hyperMILL that I can't build up in actuality, I'm gonna actually, instead of just defining a generic 12 millimeter shrink fit, I'm gonna keep it specific to different lines. So let's say I can stick it in 45. My minimal length on a shrink fit holder, I really want to get 25 to 30 millimeters in there, and the diameter is going to be 12. The shrink fit is data driven, so this diameter is important because it is going to be looking at values from other tools and extensions, so it's important that that is correct. Oh, I'm sorry, let's hop back in there one more time. Couplings, we need to find our top coupling. Adapter, new. We're going to call this one HSK 63A. Gauge point offset's going to be 0 because this is a face contact tool holder, as is all HSK. And why do we care about this? Well, one of the tabs you're going to see up here is spindles, and we can actually do a revolve function on our sort of spindle geometry, and hypermill will use that if it's defined as part of the tool during calculation of the toolpath at the toolpath level. Hypermill is always going to use your machine's solid model at the simulation level, but it's not calculating the toolpath and doing collision avoidance with your machine's solid model. So the more solids and data we can give it at the toolpath level, the better chance we have of getting to the simulation level and being collision free on the first shot. So 0 gauge point offset. Oh, so sorry. We need to define our HSK top so that it will only made up to spindles we have defined in our spindles tab as HSK 63 spindles. So now when we come back in here, we can say, okay, our top is an adapter, HSK 63A, and our bottom is a shrink fit. Those were the default values because that's all we have defined right now. We did glance over, you can set a maximum feed rate. The reality is that we're not meeting the maximum feed rate of these machines. You can also put in, you see these are all one-to-one factors for speed, feed, and depth and width of cut. If you're using a particularly long holder, or if you're getting into stuff with angled heads or anything like that, you know that we're only able to use a portion of the tool's feed and speed data, and those can just be defined really simply here as 50% of whatever it was programmed at. Okay, we'll hop onto our last tab for today, NC tools. So this is where we're going to combine tools, extensions if we have any defined, and holders to create tool assemblies usable inside of hypermill, totally built out. So um, you can go new tool and build it out from here, and then go back and select the tool. The way I sort of like to do it, because usually I have my tool in my hand first, and that's where I'm starting from. I actually come back to the tools tab. Um, I'm going to right click this, and I'm going to click create NC tool. So it's brought me back over here. This is an NC tool now. I can, when I go to select a tool from hypermill, it's going to show me this first. And then I can apply some stuff to it. I don't have an extension at this point, but we do have a holder. So we can click on this and click select holder. Now, today we just had our one holder show up, but because we've defined correctly our tool shank and our holder's bottom adapter, we'd only see this holder among the handful of others that were suitable. If we had 50 other holders in here, it's not going to show them all to us. It can save you a ton of time. We can select the tool. It's going to automatically give us a stick out that falls somewhere in that range that we defined earlier, 30 to 57. 38 seems suitable. Now it's as simple as clicking the little save icon here, and we have our first NC tool assembly. At the top, we can assign a number and ID. These may or may not be useful depending on how you have your tools called. If you had it called by name, then the tool had to have been defined in the machine with this entire name here. If it's a number, it's going to use that number. IDs are important, but for reasons we're not going to cover today, sort of with tool redundancy and automation and kind of where we're headed in the future. But that's a brief overview of putting some tools together inside hyperMILL. We'll come back sometime and take a little bit deeper depth and dive into it and talk about some of the more advanced milling formulas we can come up with and how we can work with extensions and spindles and maybe even jump into some lathe stuff. If you guys have any questions, shoot me a message right here. You can also find me on LinkedIn and on Instagram, Mickey Six Gear. All right, enjoy. Take it easy, guys.